In today's video, I'm diving into an exciting yet often misunderstood topic: the real impact of AI and machine learning on scientific research. You see, there's a lot of hype out there about how AI is revolutionizing everything, solving problems faster and more efficiently than ever. But is that really the case? A recent study published in Nature Machine Intelligence by researchers from Princeton Plasma Physics Laboratory and Princeton University took a closer look. They compared machine learning methods to traditional numerical methods for solving fluid-related partial differential equations, or PDEs. These equations are crucial in many scientific fields, like plasma physics, which is key for developing fusion power. The findings were eye-opening. The researchers found that comparisons were often biased in favor of machine learning methods. Negative results, where machine learning didn't perform as well, were consistently underreported. This paints an overly optimistic picture of AI's capabilities. Amar Hakim, a principal investigator on the research, said, "While machine learning has great potential, the literature often exaggerates its effectiveness in solving these types of equations." So, what's the catch? The study highlighted two key issues. First, many journal articles compared machine learning methods to weak baselines, numerical methods that were not the most efficient. Second, they found a fundamental trade-off between accuracy and runtime. Spend more time on a numerical method, and you'll get a more accurate result. Many papers ignored this trade-off, leading to skewed comparisons. Nick McGravy, the lead author, stated that for machine learning methods to be truly useful, they need to outperform the best numerical methods, not just any method. Yet, most comparisons were made against slower numerical methods. To address these issues, the researchers proposed two rules: compare machine learning methods to numerical methods of equal accuracy or runtime, and use an efficient numerical method as the baseline. Out of 82 journal articles studied, 76 favored machine learning, but 79% of them had weak baselines, breaking at least one of those rules. What's driving this? McGravy suggests it's the academic publishing incentives. Researchers want impressive results to get their papers accepted, which sometimes means comparing their machine learning models to subpar baselines. Publication and outcome reporting biases also play a role. Negative results often go unpublished, or unflattering data gets discarded. This creates an illusion that machine learning is more effective than it actually is. So, what's the takeaway? While there's certainly potential for machine learning in scientific research, we need to set realistic expectations and push for fair comparisons. As Hakim says, if results seem too good to be true, they probably are. Hopefully, this study will set the stage for more principled approaches in the future. Stay skeptical and always dig deeper. Thanks for watching. Don't forget to like, subscribe, and hit the bell for more deep dives into the tech world.